Hello and welcome back everyone to our second seminar for the Australian Geometric PDE seminar series for this year. Recall that we're looking at mean curvature flow with a view to understanding mean curvature flow with surgery. I'm pleased to have Marcus Flook back giving us a second talk, and Marcus is going to continue talking about the basics of mean curvature flow. Thanks, Marcus.
Thank you very much, Tim, and thank you to the organisers, Glenn, Paul and Tim, for organising this event. So for the first little bit, I just want to quickly reintroduce some of the basics of mean curvature flow that we went through last week. Again, feel free to ask any questions as we go along. So recall that we defined mean curvature flow as a smooth one-parameter family of embeddings satisfies mean curvature flow rather, if the time evolution of our embedding evolves in the direction of the normal vector with the speed controlled by the mean curvature. And in what follows, we're going to let the calligraphic M denote the embedded hypersurface at time t. So last 2 weeks ago now, we went through a few examples. So we had the shrinking sphere and the shrinking cylinder. We found that they existed for a finite time. And then we also briefly explored some graphical examples, and in particular looked at this following example where we were able to give an example where there's a singularity that we should have some kind of reasonable expectation that we can evolve past this with an appropriately defined surgery. We also looked at how geometric quantities evolve. So in particular, we looked at, say, the metric would evolve by -2 times the mean curvature times the second fundamental form. We looked then at how the area form evolved to be negative h squared, the area form. And we used this to show that when we had a compact embedded hypersurface, that the area was always going to decrease under mean curvature flow. Another nice geometric result was the evolution of the normal vector, which evolves in the direction of the tangential gradient of the mean curvature. And then in an effort to figure out how the mean curvature evolved, we computed the evolution of the inverse metric and the second fundamental form, which is expressed in this way for our case. We can obviously express this differently depending on the use that we want, but this allowed us to arrive at the following evolution equation for the mean curvature. Now, I've got 3 main goals for today. The first of which is to prove a weak maximum principle with ODE comparison. I then want to use this to prove the preservation of strict mean convexity. So by strict mean convexity, I mean that our embedding has strictly positive mean curvature. And then finally, I want to prove the short time existence of mean curvature flow under a certain amount of conditions. Okay, so first of all, what do I mean by maximum principle? Technically, you'll more commonly see this referred to as a minimum principle, but more broadly, this is a class of results called maximum principles. So suppose we have a one-parameter family of immersions of a compact manifold. Suppose that we have a sufficiently a smooth function on the manifold and the open time interval with continuity at the closure of that at the initial time. And suppose that it's a super solution to this problem here, where we have the time derivative of u greater than or equal to the Laplace-Beltrami of u plus some tangential gradient in the direction of a time-dependent field B, plus some locally Lipschitz function from R to R. Now, when we satisfy, if our function rather is greater than or equal to phi naught at some initial time for some real constant, then this function is going to be greater than or equal to phi t for all points on the manifold and for all times at which this solution exists. And in particular, this phi t function is a solution to the ODE where the derivative is equal to the Lipschitz function of phi, and the initial condition of our phi function is governed just by this minimum bound that we have initially. A quick little technical lemma just to make sure that we can carry across a lot of the results that we'd be familiar with. Suppose we have a Riemannian manifold that's equipped with its Levi-Civita connection, and we have some twice differentiable function f. It attains a local minimum at this point on the manifold, then the gradient will be equal to 0 evaluated there, and then we obviously have this this Nabla squared term is going to be greater than or equal to 0. So we can prove this relatively quickly just from standard theory. If we suppose that we have some vector in the tangent space at some point on the manifold, we have our geodesic which passes through that point and has the derivative at that point at that time given by this vector, then we have that this composition of the function and the geodesic will attain a local maximum, a local minimum at this point, and so we obtain the desired equalities and the inequalities from there on. So we can use that standard theory pretty freely. Okay, so let's prove this result, just quickly going back. We're going to break this down into 3 cases and then use the previous case to prove the next one. So suppose now that we just have f is identical to 0. So we're supposing that we have a super solution to this PDE here, and that u is initially non-negative. We'll define this new function, u sub epsilon, by u plus epsilon times t plus 1 for some arbitrary epsilon greater than 0. Now this is going to satisfy the following. It's a super solution to the following problem here. We can just quickly see that the time derivative is going to give us that extra epsilon term, but the spatial derivatives will be unaffected. Now, suppose that we have some first time where u epsilon is equal to 0. So for the smallest such t, first time that this is becoming equal to 0. Well, in this case, it's still satisfying this PDE, so we can write out this expression. What we should notice, though, is that at this time, the time derivative at this point is going to be less than or equal to 0. Spatial derivative is going to be equal to 0 here, and we have the Laplace-Beltrami is going to be bigger than or equal to 0. So on the right-hand side, this expression has to be greater than or equal to epsilon. On the left-hand side, this has to be less than or equal to 0. So we arrive at a contradiction. What this contradiction in particular tells us is that therefore u epsilon has to be greater than or equal to 0 for all epsilon and for all time where such a solution exists. And so u has to be bigger than or equal to 0. Next case, let's consider f is now equal to minus c of u. So suppose, again, we have a super solution to this problem here. We just add in the f term. And again, we are initially non-negative. So in this case, let's define another function, u bar, which is defined as u times e to the ct. So hopefully you can see where this is going. We want to show that this satisfies the PDE in case 1, and then we're done. So computing the time derivative, basic product rule, we can see that we're just going to get e to the ct times the partial derivative with partial time derivative with respect to u plus c e to the ct u. Applying the fact that this is indeed a super solution, we will get this expression, and this is where we can see the terms that we want to cancel out will nicely cancel out. What I should also point out is that, yes, I've kept the e to the ct here factored out, but we can pass that into the spatial derivatives because it's just a time-dependent function. So we can see here that u bar satisfies the case given before in case 1. So by case 1, we can say that u bar has to be greater than or equal to 0 for all time where the solution exists. Now, clearly, because of the exponential, this means that u itself has to be greater than or equal to 0 for all time. So now to our general case, where we just say that F is locally Lipschitz. Suppose that we satisfy, again, we have a super solution to this PDE, and we have the minimum is greater than or equal to some phi naught at the initial time. Well, in this case, we again want to suppose that phi t solves this problem. Now, in this case, what we're going to arrive at when we find the time derivative of u minus phi, this is greater than or equal to just the super solution component of partial u minus the time derivative of the phi function, which is obviously going to be f of phi. Now, as before, I can put the phi function back into the spatial derivatives because this phi function is just a time-dependent function. So I can put that back in. What I can find then using the condition of locally Lipschitz, I can say that this is greater than or equal to this expression minus c sub t prime, where the t prime is just any t less than or equal, any t prime less than t. This will hold on this compact time interval. Now this holds any t prime less than t. So by case 2, we can say that u minus phi is greater than or equal to 0 on this compact time interval for all t prime less than t. So therefore, we get this really nice result that u at any point at time t has to be greater than or equal to phi t for all t where the solution exists. And then we're done. So this is particularly nice because when we apply it to, say, the evolution of the mean curvature, not only can we get a result which says it remains positive, we get an inequality which we now have a lower bound on our mean curvature. So let's actually explicitly look at this. So we'll call a hypersurface mean convex if it admits a unit normal. So a unit normal field with respect to which its mean curvature is non-negative, and we'll say it's strictly mean convex if it admits a unit normal field with respect to which the mean curvature is positive. So pretty standard definition. Recall as well that when we looked at the sphere and the cylinder, both of these were strictly mean convex embedded hypersurfaces. So we can think about those if you want to. So recall that we had this evolution equation for the mean curvature. Note that in this inequality, we're using the Cauchy-Schwarz. So we're showing that the evolution of the mean curvature is greater than or equal to 1 on n, the mean curvature cubed. So in this case, the locally Lipschitz function, which is going to be smooth, is f of x is equal to 1 on x cubed. Now, the associated ODE with the initial condition of just the minimum mean curvature is solved by the following problem. Solved by the following function, manipulated a bit so that we can see when this blows up to infinity quite nicely. So in particular, using this weak minimum principle, this implies that if the initial mean curvature is greater than 0, then what we have is that the mean curvature at any point at any time is bounded from below by this expression here. So this means that mean convexity is conserved. What we also get is a finite time blow up prediction, because this is going to fly up to infinity in finite time. And in fact, if you're interested in a little computation, because we have the equality of here, so we have the equality here in the sphere case, and the finite time blow up is exactly predicted by this lower bound here. So if you want to have a look, those finite time blow ups completely coincide precisely because we have the equality here. So that might be nice for people to go through. Okay, so the final results that I wanted to talk about today is basically the result that gives us a theory to talk about. So for at least some short time, we have the existence of a solution. So in the version that we'll prove today, we're going to assume that we have a smooth, closed, embedded hypersurface. Then there will exist a solution, a unique solution to the following problem, which is mean curvature flow, defined on some short positive time interval. I should make a remark that you can loosen, I believe, pretty much all of these conditions. You just have to be careful about what's happening with the other case. So we can weaken the smooth condition, we can weaken the closed condition. The example I give here is that we can, of course, weaken the embedding to an immersion, but we can also take the hypersurface and just have it embedded in higher codimension. But for our cases, we're just going to look at smooth, closed, embedded hypersurface. The key philosophy that we mentioned briefly in the first talk, but I should highlight again before we jump into the nitty-gritty of the proof, is that when we were looking at the mean curvature flow last time, we realized that it was weakly parabolic, that there was a degeneracy in the tangential directions. What we noticed, though, when we wrote this locally as a graph was that the graphical solution was a strictly parabolic PDE. So we aim to fix this degeneracy in some sense by passing the function to a height function over the initial embedding. So that's the main philosophy of what we're going to be doing. We then have to do a fair few computations to make sure that we can show that it is indeed strictly parabolic, but this is the main guiding idea that we have. I should point out as well that this proof mainly came from, I believe, Huskin and Polden as well. So let's make this precise. Writing a graph of the, so we want to write the embedded hypersurface as a graph over the initial embedding. So more precisely, we can suppose that V0P is a unit normal vector to the initial embedding. We'll define the perturbed hypersurface by this function here. So we take the initial embedding, we add on some time-dependent function times that normal vector, where of course the initial condition is that this f is equal to 0. So unfortunately, we've left the realm of Ecker drawings. I had to come up with my own poor artist rendition, but this is the general gist of what we're doing. Now, we're also going to solve a slightly different problem, which I'll call MCF star. Note that what I'm saying here is that, so we take the time derivative of this, we're left with the time derivative of the f times the initial normal vector. So this won't be the normal vector. Well, in general, this won't be the normal vector as the hypersurface evolves. So what we're saying here is I want to say that the time evolution of the mean of the embedding in the direction of the normal component is equal to the mean curvature. So there could be, and there likely will be, some kind of tangential component here. If I rearrange this expression, I can get us into a nicer form where we have the time derivative of the f function is equal to the mean curvature divided by this product of the initial normal vector and the evolving normal vector. Now, the aim that we have at the moment is we want to express this right-hand side in terms of f and show that it's strictly parabolic. Now, of course, to do this, we're going to have to compute the induced metric, the second fundamental form, and the mean curvature of the perturbed hypersurface. Now, to make the notation a bit less scrappy, I'm going to let G tilde and the second fundamental form tilde is the metric and the second fundamental form of the initial hypersurface, so at time 0. And I'm also going to let f sub I be the spatial derivative in the direction of I of f. So if we look at the spatial derivative of the embedding, we're going to have the spatial derivative of the initial embedding plus the derivative of f times this normal vector plus f times the spatial derivative of this normal vector here. Now, one of the things that we discussed last week as a nice trick to compute the evolution of the normal vector was that this derivative has to be in the tangent space of the original embedded hypersurface. So what this means is that we can write this as a linear combination of the tangent vectors of the initial hypersurface, obviously taking the trace over the initial metric. And what we hopefully notice here as well with this term here is that this is looking at giving us the coefficients of our second fundamental form. So again, this is the second fundamental form on the initial hypersurface. So one very nice expression here that we should point out is that the first and last term are expressed with respect to the tangent vectors of the initial hypersurface, and then this is being expressed with respect to the normal vector of that initial hypersurface. So to find the induced metric, what we want to compute is this dot product here. So we can see already that if I write this out in one go, it's going to get pretty nasty pretty quickly. So I'm going to break it down as best I can. So this is just what we computed last time. We want to obtain what this is. So first thing that we should point out, we get this nasty expression. I might try and use the annotation. First thing that we can simplify is that only these terms are going to be normal with respect to the initial hypersurface. So immediately I can use the orthogonality and the fact that we have the linearity of the product to give us this, to give us this still nasty, but slightly nicer expression. So now we're just working with the tangent vectors here. And I'm going to call this asterisk so we can simplify this again even further. Okay, so I'm going to break this down term by term so we can understand it hopefully pretty clearly. This first term, if we just again use the linearity, we just want to be taking the standard dot product that we have, we get the initial metric on the hypersurface. That term, pretty straightforward, pretty simple. Now the next term, obviously considerably more nasty. What we're looking at here is these coefficients. So these terms here. So we're going to have the f squared, the two metrics on the initial hypersurface, second fundamental form, but we get this nice expression here, which we can express as the initial metric, which we'll hope to simplify as we go on. Oops. Now, if we look at the next term, here we're just taking this term here, being dot product with this term. Again, we're hoping to get a very nice expression for the initial metric. And of course, by symmetry, we can see what the next term is going to be. So we can evaluate that fairly quickly. So in the next step, we basically just want to substitute all of these initial metrics into the system and see what we get. So looking at this first term, we have the initial metric with the indices Km, with Kj, and with Mi. Now, clearly, we can contract these. We can use the Kronecker delta relation with the inverse metrics, which will greatly simplify these expressions, in particular, these last two terms. So if we were to say, I might give this in a bit more detail, we look here at the GKN, GKJ. This is just going to be the Kronecker delta of NJ. So that means that this second fundamental form, if I add this in with IN, is just going to return the IJ. So I should have that second fundamental form there as well. But we can see why these are both going to simplify to this same component here. Now, in this case, we are doing a similar simplification with a bit more terms, and we'll further simplify it again by doing a contraction there. So we're just contracting one of the second fundamental forms here. So if we bring all these terms back together, it's actually a relatively nice form that we can look at. In particular, the main message that I want to get across is that the way that the metric evolves over time is just a small perturbation of the initial metric, provided that the C1 norm of F is sufficiently small. So this is particularly nice for our purposes. So again, we need to compute the normal of the perturbed hypersurface. This isn't too difficult for us, actually. So recall that we have our tangent vectors here. So all we're doing here is we're taking the initial normal component and we're getting rid of all of the components that are tangent with respect to this new tangent space. So we're just making sure that as we evolve through, we're slightly modifying the initial normal vector so that we remain normal. Now, again, hopefully one thing that you've been able to see here again is that if we look at, so what I should make clear is that partial Ix is this partial Ix here. What we can notice is that all of these terms here and here are going to be orthogonal to the initial normal vector. So the only component that we're left with is this ith derivative of f. So we can simplify this again to get this form. Again, what this is telling us is that the normal vector, as it evolves, is only going to be very small perturbations of the initial normal vector. So again, small perturbations. More explicitly, just because this would be important as we're going to be dividing by this upcoming quantity, in particular, note that for all epsilon greater than or equal to greater than 0, there's going to exist a delta such that if the C1 norm is bounded above by delta, then the difference between the dot product, I should have dot product there, sorry. So the dot product in Rn minus 1 is going to be less than epsilon. So we can make these sufficiently close to each other, provided we have a nice upper bound on C1. So we're mainly noticing that provided we have a good bound on the C1 norm of F, this problem is controlled very well. Okay, so again, just stating our tangent vectors. We want to compute the second fundamental form of the perturbed hypersurface, remembering that the end goal is getting to our expression for mean curvature, which is just the trace of our second fundamental form in the way that we're working. So this is the end goal that we're trying to get to. Okay, so let's consider what. So this is obviously a very gnarly expression. Most of the time, it's just applying just your standard product rule techniques, nothing too difficult there. The main aspect that I want to highlight is that we have, so when we were looking at the initial PDE, we have PDE that looks like this, where we have the initial normal vector and the new normal vector. The fact that we see this term here, partial I, whoops, that should be partial j, my apologies. Yeah, sorry, so this term here, I might just quickly fix. This term here should be partial I, partial j of f. The fact that this is appearing here is a very good sign when looking at this, because ideally, we want to have some nice elliptic component here, say taking the trace of those derivatives plus some nice expression here. So this is a really good sign. These components we're not too worried about. We just need to be able to sufficiently control them as time goes on. So this is a very good sign from the perspective that we had at the start, trying to write this as an expression of f. So I'll quickly get rid of that, but I'll keep on this expression that we have here. So it looks like it's fixed in this next step, which is nice. So what we have is a component which is the normal vector at any time, dot product with the initial normal vector, times the second derivatives of f plus some nice smooth expression, provided that, again, the C1 norm of f is nicely bound. Okay, so again, we're looking with an eye towards the mean curvature. The mean curvature of the perturbed hypersurface is just given by our trace of our second fundamental form. So in this case, things are looking, so simplifying on this side, we've bunched all of these terms together from before. And now this P term is being defined as the trace of those Pij. Again, this is smooth, provided that we have a nice bound on the C1 norm here. So this is a very nice elliptic term. This is also particularly nice because remember that initially in our expression, we were looking at the derivative of f is equal to h divided by the initial normal vector and the evolving normal vector. So this appearing here is a very, very good sign. Oops. Okay, so yep, all we're doing here is passing through the trace. Now, here we're going to divide both sides by the dot product of these two normals. Now, this is where, in particular, making sure that we could always make sure, if I get my pen back, that the dot product between these two terms is always sufficiently close to 1, meaning that we can maintain the fact that this Q function is going to be smooth. Now, rearranging the initial PDE that we had, so we started off with this PDE here, which was, just to highlight, this wasn't, sorry, it's already there. This was the mean curvature flow star. Now, of course, in this case, we can express it simplifying here for the mean curvature terms by this very nice elliptic component here and a smooth component here, provided again that the inputs are sufficiently small. So what we've arrived at is a quasi-linear, meaning that it's linear in its second order derivatives, but it could be non-linear in these components here, strictly parabolic PDE, so we can obtain a unique solution on a short time interval by relatively standard theory. I might quickly ask if there's any questions at this point. Now, one thing I should note is that we haven't proven short time existence to mean curvature flow. We've proven short time existence to this other PDE, where we were specifically taking the evolving normal component with this time derivative. But there could be some tangential motion, which is making this different.
So, Max, it might be good to mention here that the Gij on the right-hand side of that equation you just derived also depends on f, right? And derivatives of f.
Yes, and time. Yep. Yeah. And the derivatives of f. Yep. So it would probably be more informative in a nice way to express that this is, amongst other inputs, depends smoothly on the time argument and f.
So just f, no derivatives of f?
I can quickly skim back to where we derived it.
Sorry, I can't remember.
No, it's all right.
There it is. Yeah.
So there was, yes. So thank you for that, because that actually means that a much better way of writing this would
Yes, I guess the absolutely crucial thing is that there are first derivatives there, but no second
Yes.
derivatives.
Yeah. So this would probably be the most informative way to express it. And if I go back to the original expression, hopefully that still fits in nicely. Yep. So again, that C1 norm is the one that we need. Okay, so moving forward, we have a solution to mean curvature flow, star. However, what we could have is some kind of system, say, in a sense where we could have some kind of sphere. And what's actually happening is that the evolution of this satisfies some equation, which is the mean curvature, but there's some tangential component. So we could imagine that it is indeed shrinking, but what's happening is that it's also rotating as it does. So what we want is, with a solution to mean curvature flow star, can we get a solution to the mean curvature flow where we don't have this tangential component? And this initial drawing might be a bit nice to think about, because if we have, say, okay, so suppose we have a short time solution to this following system, where we have, this is our tangential vector field. So this is the term that's making it different from mean curvature flow. So we've proven the existence of this problem. Now, what we're going to do is we're going to make the ansatz that we have a family of self-diffeomorphisms. So a one parameter family of diffeomorphisms, which we'll call the time dependence. And suppose, so the basic idea of this is that if we have a solution, say, to mean curvature flow star, where there's the, say, very basically there's that rotation, we want to counteract this with the family of self-diffeomorphisms. So making the ansatz of the solution is just the solution to mean curvature flow star, but we're composing it with this one parameter family of diffeomorphisms. If we compute the time evolution of this, just getting rid of that red component there, then we have the time derivative of the embedding itself, but we also have to make sure to include the derivative here times the derivative of the time-dependent diffeomorphism. So this component, the first term here, we can simplify just by what it is by definition. So this first component just becomes this term here. All we're doing is substituting in the fact that it solves mean curvature flow star, but we still have to deal with, we still have to deal with this term here, which is meaning that we can, in some sense, try and cancel out this tangential motion. So clearing that, what we arrive at is that this is equal to this term here, if and only if the time derivative of our family of diffeomorphisms satisfies this equality here. So what we're trying to do is, whatever tangential motion we have, we're trying to construct a family of diffeomorphisms, which is reversing that. And by relatively standard ODE theory, a solution to this exists, and it will be unique. So this means that by the previous working that we had a few slides ago, we have a unique solution for the short time existence for mean curvature flow star. Now, with this new bit of theory that we have, we can use this family of diffeomorphisms, which is guaranteed to exist and be unique, again on a short time, to move us into a solution to mean curvature flow. So with the existence of this, we can now satisfy the equation of mean curvature flow with no tangential component. So as such, we've shown that we have the short time existence of the mean curvature flow itself. I should mention as well, there's a lot of ways that you can prove the short time existence. This is just one way, which is particularly nice because it refers back to what we were talking about in the first lecture, where we were making reference to passing to the height function in some sense removes the degeneracy. We can use that quite nicely here to show the existence. Similar techniques are quite nice for, say, the avoidance principle and so on and so forth. Do we have any questions on that particular proof for short time existence?
Marcus, I have a question. I'm really sorry if I wasn't paying attention to this, but did you say why that dx thing is invertible?
So for our case, it's going to be invertible from it being an embedding.
Oh. Yep, good. Sorry, I thought you were doing something else there.
T is tangent to the surface, to the hypersurface, right?
Yes.
So if T would be normal, then it doesn't make sense, but T is on the surface, so it's just, you know.
Yep. Yep.
So yeah, so you're pointing in the right direction, I suppose, to get that.
Yep. Yep. Those are the main three things that I wanted to cover. So if there's anything that people want to explore in more detail, or if there's any questions, I'm happy to go back and explore them in a bit more detail and potentially talk about what we'll be looking at in future weeks. But for now, thank you very much again for your attendance, and thanks to everyone that gave me feedback on the previous talk, and hopefully I've made some nice additions to the text slides. But thank you very much again, and let me know if there's any questions.
Well, let's thank Marcus for an excellent talk and for going through all of these significant computations for us. As Marcus suggested, we'll now open up for questions or comments if you have any.
This isn't a question, but is there any chance you could put the slides up on the Zulip chat? I'm using them for a reading course.
Yeah, sure. What I'll do to make sure I'm not giving you a massive PDF, I'll get rid of all the pause features so that it's not 100 slides, and then I'll send them to Tim potentially, and he can put them online.
I'll then send them to Paul, who will put them online.
Yeah, but I'm more than happy to put them online and make them available. Yep, no worries.
Thank you so much.
All right, in the absence of any further comments or questions, let's thank Marcus again for some excellent talk. All right, thanks guys. We'll leave it there. We'll probably aim to do the next talk in about 2 weeks from now. And the intention is to have Adam Thompson speaking. So tune in next time. Thanks, everyone.
Thanks, everyone.